Hello, I'm Matthew Meininger. I've put this video together to try and answer some questions that I've had during my time discussing nuclear power, as well as climate change in the environment. I'll go over the fundamentals, electricity, renewables, nuclear power, the types of nuclear reactors out there, radiation, Chernobyl, Fukushima Daiichi, safety and risk, nuclear waste, climate change in the environment, and hopefully try and answer some common questions out there. So my name is Matthew Marger. I work at Darlington Nuclear Power Plant, and I'm also the Canadian Operations Officer at North American Young Generation Nuclear, which is a nonprofit pro-nuclear group out there with 120 chapters all across North America. My background is nuclear engineering, so I graduated from nuclear engineering in 2014 from the University of Ontario Institute of Technology, and I'm a professional engineer in the province of Ontario. I've worked in the nuclear industry for almost 7 years now in a variety of roles, from reactor safety to minor modifications to stakeholder relations, also performance engineering, and really just made this video because I saw a gap in kind of tying it all together, advocating for nuclear, why I believe in it. So hopefully it answers some questions. So really want to start with the fundamentals. Energy is the ability to do work, and power is the rate of change of energy, so energy divided by time. I think we hear these words quite a few times used in the same context, but those are the differences. And most energy that people use is actually derived from nuclear. So fossil fuels come from ancient living things which receive their energy from the sun, which is powered by nuclear fusion. Biofuels and solar power are also the same, and wind power is a result of the difference in air density caused by the unequal solar heating. Geothermal energy comes from radioactive decay of heavy elements such as uranium and thorium. So everything is really as a result of the sun, which uses nuclear fusion. So some differences between solar, wind, geothermal, hydro, bio, coal, and nuclear. Solar really uses solar radiation, changes that into electricity. Wind uses the turbine to change mechanical energy into electrical energy. Geothermal heats water, which turns a turbine, which turns a generator, which makes electricity. Hydro is very similar. It's churning that turbine, having water flow past it, which is connected to a generator to make that mechanical energy into electrical energy. Coal and nuclear work very similar as well. You're heating water, that water turns to steam, that steam turns the turbine, which is connected to a generator, which produces electricity. So everything is very similar in how it produces electricity from a basic standpoint. And burning fossil fuels releases chemical energy in which chemical bonds holding atoms together are broken. And on a per mass basis, nuclear reactions release more than 1,000,000 times more energy than chemical reactions. That's the real difference. Is in nuclear, you're separating the atom itself. You're not just splitting off the electrons, you're physically splitting the atom itself. So that releases 1,000,000 times more than the chemical reactions because you're splitting the nuclear strong force. And nuclear fusion releases 3 times more energy than fission. So fission is splitting, fusion is putting together. For electricity, for storage, storage does add quite a bit of cost. So a recent comprehensive analysis found that the cost of adding just 10 hours of storage would nearly double the cost of electricity. Also want to talk about the different types of base versus intermediate versus peak load. So baseload is essentially what you rely on every day. It doesn't matter if it's the middle of the night or the morning. It's the energy that we always need. So those are the hospitals, the baseload things that we need for our life. So that's really coal, nuclear, hydro, geothermal, biomass, and biogas. We have something called intermediate load, which is as more of us wake up, the load shifts, we need more power. So solar and wind can be good factors for that. And peak load is on a hot summer day, in the middle of the day when everyone has their air conditioning running, we have a peak load, and that can be oil or methane gas, which are really able to ramp up instantaneously, can shut down when not needed. So they're available on an as-needed basis, and that's really what people refer to when they say peak load or base load or intermediate load. And currently, 1 in 7 people in the world have no access to electricity. So there are still a lot of people out there with no access to electricity. And the projected worldwide consumption of all types of energy 30 years from now is about 50% higher today. So we do hear people talk about conservation of energy and how we can have more energy efficient products. And that will reduce in the developed world the electricity. But for the developing nations out there, they are still going to need a lot more electricity, still need a lot more energy. So that's where we see this huge demand coming forward. And that's really why climate change, we're going to have to look at these energy sources, get the clean energy sources, because the developing world is going to need a lot more energy. In terms of renewables, Germany had more than 100 times in 2017, sometimes for more than a day at a time, they had their electricity prices go negative, which means that the grid operators actually paid large consumers as much as 6 cents a kilowatt hour to take power to avoid overloading the grid. So that is the one interesting thing with renewables, is as we get these peaking loads, they can actually disrupt the grid operation, make it much more complex. And over the past decade, the world has spent $2 trillion on wind and solar power. We've seen almost no progress towards decarbonization. So in 2017, fossil fuels generated almost 65% of the worldwide electricity, whereas 62% in 1990. So we are seeing a greater shift towards fossil fuels, and that's quite alarming. So while the reductions in wind and solar costs continue, which I hear quite a bit, that the costs keep coming down, the rate of decline has slowed, especially for onshore wind. So again, there's these asymptotic shifts where you can keep reducing the cost, but at some point, every effort towards it doesn't have the same rate of return. And more often, rather than vent steam from a coal plant, electrical grids will curtail wind or solar power, wasting their potential output rather than letting it onto the grid. This, in particular in China, have affected their wind farms, where curtailment has recently caused a reduction of about 20% in wind power generation of the country. Interesting statistic is called a capacity factor. So capacity factor is really how often are things operating divided by how often would they be available. So when called upon, how reliable or how often are they actually doing what they're supposed to be doing. So wind has a capacity factor of just under 23%, and solar power was around 13%. So again, these are intermittent sources, and they need to be backed up with fossil fuels, such as gas plants, to provide that constant power. So a serious grid integration problem with solar is that cloud cover can reduce the output by 70% in the space of 1 minute, so a drastic drop, which again further complicates the grid and the integration of solar into that system. And something that I haven't heard talked about too much at all is the lifespan of solar and wind. So the lifespan is around 20 years, whereas nuclear power plants are 60 to 80 years right now. IRENA in 2016 estimated that there was about 250,000 tons of solar PV waste, and that the total could reach 78 million tons by 2050. Solar recycling is generally not economic, and there is also concern about cadmium leaching into the ground from discarded panels. And the hidden costs of integrating solar onto the grid add about 50% to the standard cost of solar power. So unlike nuclear power, the cost of decommissioning solar farms are not usually included in the price. So there's a lot of hidden things in the background here. I want to talk about nuclear power a bit as well. So uranium comes from the earth. It's mined, it's milled, it's converted. It could potentially be enriched for some power reactors, and then it's fabricated into fuel. And the fuel is uranium dioxide. So it's a ceramic pellet It's usually quite small. It's usually black in appearance, and it's actually safe for workers to handle. So people are working with natural uranium and uranium dioxide pellets every day in the fuel manufacturing facilities, and they just wear cotton gloves so they don't get contamination on the fuel pellets. Nuclear energy comes from transforming matter into energy. So an individual neutron or proton always has a greater mass outside a nuclear nucleus than inside. The mass difference comes about because when the neutrons and protons bind together, a tiny fraction of their mass is actually transformed into energy, which is the binding energy. So Einstein related that energy and mass are the same thing. They can be converted from one to the other. So that's really how it generates the heat. And the average nuclear power plant is around 1,000 megawatts electric, and it can generate the electricity demand for about 600,000 people. So, for example, at Darlington, it's just over 3,000 megawatts electric. At the Pickering nuclear site, it's just around 3,000 megawatts electric. So it's a very small site, but producing power for 1.5 million people or more. And a single pellet, like I said, that small little pellet contains as much energy as 1,000 kilograms of coal. So its energy density is just so much more compact. It's so high for the energy density. Now, there are many different types of nuclear reactors out there. They're called generation types. So there's generation 1, which was the early prototypes such as Shippingport, Dresden, Fermi, Magnox. And then really what we have mostly in the world is generation 2. So that's a second generation nuclear reactors. Those are the pressurized water reactors, the boiling water reactors, the CANDU types, the VVERs, the RBMKs, the AGRs. So many acronyms here, different processes. There's also generation 3s that are out there. Those are the APRs, the ACPRs, the ABWRs, the EC6, the AFCRs, so lots of acronyms, lots of different designs out there. And then there's Generation 3 Plus, which really popular one is the AP1000. There's also Generation 4 reactors that are being developed, so those are the sodium fast reactors, molten salt. Really, their difference is using high temperatures can mean the production of hydrogen and the synthesis of carbon neutral fuels. So sometimes I hear the anti-nuclear groups out there say that there's no development in nuclear, and that's absolutely not true. Just mostly what we have right now in the world is the Generation 2, but since those were developed in the 60s, there's been a tremendous amount of learning experience, design changes, and safety increases, as well as efficiency gains that have been done. So small modular reactors are something being talked about right now. They can use existing nuclear technologies, or they can use the new Generation 4 designs, and the coolant systems can use natural circulation, which is a passive way to control it. So the small modular reactors, unlike the big power plants, can be built in isolated communities. They can be built in mining communities. Because they're modular form, you can add them as you need them. So again, it's opening up new markets for nuclear to be part of reducing fossil fuels. And like I said, there's so many different ways these work. Some use enriched uranium, but it's very low level enriched. Some use natural uranium, such as the CANDU technology. And what the CANDU technology does is they use heavy water, so their moderator is different, where their natural uranium is different from other designs. So I just want to talk about radiation. So radiation is just a form of heat transfer. So there's three main types. There's conduction, which is the transfer of thermal energy through direct contact. There's convection, which is the movement of liquid or gas, which is how your radiator at home works. And there's radiation, which is through the electromagnetic waves, and therefore does not rely on contact between the heat source and the object. I think a lot of times what people mean is ionizing radiation. So ionization means that the radiation's energy can produce ions, which are charged atoms, by knocking the electrons off of neutral atoms. So longer wavelength, lower frequency waves such as heat and radio have less energy, and shorter wavelength, higher frequency waves such as X-ray and gamma rays. So not all electromagnetic radiation is ionizing. It's only the high frequency portion of the spectrum, which includes X-rays and gamma rays, that are ionizing. So alpha and beta particles are considered directly ionizing because they carry a charge, and therefore when they interact with the electrons, they directly impact that, they ionize it. The neutron is an indirectly ionizing particle because it does not carry a charge, but ionization is caused by charged particles which are produced during collisions. And the third type is X-ray and gamma rays, which are electromagnetic, indirectly ionizing radiation. They're indirectly ionizing because they are neutral and do not interact with the electrons through Coulombic forces. So humans have used uranium oxide since at least 79 CE, and on average we're always receiving radiation. We receive on average between 2 and 3 millisieverts of radiation every year. So to put that in perspective, I'll give some examples. So a dental x-ray is 0.005 millisieverts. A 135 gram bag of Brazil nuts is 0.01 millisieverts. A transatlantic flight is 0.07 millisieverts. A CT scan of the chest is 10 millisieverts. And smoking a pack and a half a day for a year of cigarettes is 36 millisieverts. So radiation is actually a relatively weak carcinogen and mutagen, and it's important to remember that over the population, a third of the population will just naturally get cancer. So the International Commission on Radiological Protection stated that there is no deterministic effects would be expected below an absorbed dose of 100 milligray. And the threshold for most effects are much higher. So the estimates that 200 millisieverts raises the risk of a fatal cancer is 1%. So again, it's always interesting to put this in perspective. So there were 545 nuclear weapons tested atmospherically up until 1963. The global peak average was 0.113 millisieverts in 1963. So again, bring that back to how many Brazil nuts or how many flights you need to have that equivalent. And there are just different places in the world that have background radiations that are much higher. So in Ramsar, Iran, residents can receive doses up to 260 millisieverts per year, which is almost 100 times the global average due to naturally occurring radioactive elements. However, there's no evidence of any adverse health effects from these areas. So the average source of radiation for an American would be 40% from radon, which again, if you go into basements, there's higher levels of radon there. 18% comes from the buildings or the soil, which have naturally radioactive isotopes in them. 14% from cosmic radiation. A small portion of 11% from food and drinking water. So, for example, bananas have radioactive potassium-40, Brazil nuts, there's a number of key naturally occurring ones out there. 14% from medicine, and 1% from the nuclear industry. So that's the makeup. And fly ash emitted from coal actually carries into the environment 100 times more radiation than a nuclear power plant producing the same amount of energy. So again, it's things that we don't really think about, but radiation is all around us. It's everywhere. It's part of life. I want to talk about Chernobyl. So Chernobyl accident in 1986 was a result of a flawed reactor design that was operated with inadequately trained personnel. So 134 staff and emergency workers suffered acute radiation syndrome due to the high doses of radiation. And of those, 28 later died from that acute radiation dose. Almost 6,000 people continued to work at the other Chernobyl units every day until Chernobyl Unit 3 was decommissioned in 2000. And their radiation dose has been within internationally accepted limits. So even though Pripyat and other areas are closed off to visitors, they were working right beside the unit at Chernobyl up until 2000. So the United Nations Scientific Committee on the Effects of the Atomic Radiation says that apart from increased thyroid cancers, there is no evidence of a major public health impact attributable to the radiation exposure 20 years after the incident. Thyroid cancers is usually not fatal if diagnosed and treated early. The report states that of the diagnosis made between 1991 and 2005, 6,848 cases, 15 of those proved fatal. And a big thing with that was the government refused to give potassium iodide tablets out to children after the meltdown. So again, it was a very different time. It was during the Cold War, and Russia wanted to maintain secrecy and control over the plant when it happened. Fast forward to Fukushima Daiichi in 2011. So the initial estimate from Japan's regulators stated that Fukushima released about 15% of the amount of activity released in Chernobyl, and later this was refined by the Nuclear Safety Commission to 11%. So again, a very different release type of magnitude than Chernobyl, which I don't think a lot of people put perspective to. And TEPCO figures submitted to the NRA for the period to the end of January 2014 showed that 173 workers had received more than 100 millisieverts, and that just under 16 had received 50 to 100 millisieverts. There were no radiation casualties, which is acute radiation syndrome, and there have been no fatalities from the nuclear accident. The United Nations Scientific Committee for the Effects of Atomic Radiation stated that adults living in the city of Fukushima were estimated to have received, on average, an effective dose of about 4 millisieverts, which is again just slightly higher than the normal background that you would expect. And there have been no discernible increased incidence of radiation-related health effects among the exposed members of the public or their descendants. So annual exposure in the region is around 2.1 millisieverts. So again, it's all about putting these doses in perspective and seeing how they relate to, for example, how many bananas or how much Brazil nuts. And the World Health Organization report indicated that the residents of the area who were evacuated were exposed to so little radiation that radiation-induced health effects are likely to below detectable levels. So the main cause of death was the tsunami, the earthquake, as well as the fear of radiation, which caused a lot of people in Chernobyl and Fukushima to have anxiety, to have abortions, to have all these other health effects not actually caused by radiation. It's the fear, it's the unknown, it's that's the real cause there. In terms of risk and safety, I just want to make it clear that the operators of nuclear power plants are liable for any damage caused by them regardless of fault. So there are actually insurance companies out there. They therefore normally take out insurance for third-party liability. In most countries, they're required to do so. In terms of risk and safety, I think the best way to put this in perspective, since humans are so bad at quantifying risk and safety, you see it after a plane crashes. It could be the safest form of travel, but after a plane crash occurs, people are reluctant to travel there, even though they're much more likely to get into an accident driving to the airport than they would actually flying. So it's something called the death footprint. And really what this is it takes the worst case, Chernobyl, Fukushima, all the worst case estimates, and it says deaths per trillion kilowatt hours. So it's putting it in an objective, deterministic type of view to look at risk. So coal, the global average, has 100,000 deaths per trillion kilowatt hours. And this is because coal has such a well-known health impact for respiration, so causes direct lung cancers and throughout the world. Oil is the next highest at 36,000, biofuel at 24,000, gas at 4,000, hydro is at 1,400, solar at 440, wind at 150, and the safest is nuclear. And again, that's taking the worst case scenarios for Fukushima, 3 Mile Island, Chernobyl as well. And one surprise to people is hydro. That's because, for example, one One hydro breakdown in China in 1976 killed 171,000 people. So when you look at the power produced, that's how that number gets higher. And for solar and wind, that's the mining, that's the shipping, that's the treatment there. And there are still one-off cases where people fall off windmills. And again, since wind and solar haven't produced that much power, that's why their death footprint is quite a bit higher than nuclear. But again, well below coal and oil, so much safer than those. So data compiled in the U.S. Bureau of Labor Statistics shows that it's safer to work at a nuclear power plant than it is in the manufacturing sector, leisure, and hospitals, and even the financial sector. So again, it's something that that has the highest safety because people think it's unsafe. It's just like a roller coaster. It looks unsafe, but it's actually quite safe once you look into it. In regards to nuclear waste, so unlike other hazardous industrial materials, the level of the hazard of all radioactive waste, its radioactivity, diminishes over time. So a toxic material that you dispose of is toxic forever, where radiation actually diminishes over time. That's the half-life. Half of the radiation is gone at that point in time. So a spent fuel assembly will approximately consist of, by weight, 95.6% uranium, just under 1% of plutonium, under 1% of minor actinides, and around 3.5% fission products. So a lot of what we consider spent fuel has a lot of uranium still left in it, a lot of energy still available to it. In terms of nuclear waste composition, 90% is what we consider low-level waste, so that's lightly contaminated items like tools and work clothing, and these contain only 1% of the radioactivity. The next level is called intermediate level waste, and that's 7% of the composition. So this is used filters, components within the reactor. This contains 4% of the radioactivity in nuclear waste. And the last category is high-level waste. So this is spent fuel, which contains 95% of the radioactivity. So again, there's quite a change there. So if nuclear power was used to supply a person's electricity needs for an entire year, only about 5 grams of highly radioactive waste would be produced. It's the same weight as a sheet of paper. And many times people don't think reprocessing has been done, but this is used extensively through European countries, Russia, China, and Japan. The pro is that 25 to 30% more energy can be extracted, and it reduces the volume of high-level waste by around 85%. The con is it's immobilized, so it's a one-and-done type of process. So after it's been reprocessed, it's usually locked up in unusable form for future use. They also have electrometallurgical and pyroprocessing, and they have these new reactor technologies, so integral fast reactors, breeding reactors, traveling wave reactors, that can actually take spent fuel and use that as fuel in the process. That's a closed fuel cycle. So there's a strong technical incentive to delay the final disposal of high-level waste for about 40 to 50 years after removal. So at that point, the heat and radioactivity will have been reduced by over 99%. After being buried for about 1,000 years, most of the radioactivity will have decayed. The amount of radioactivity then remaining would be similar to that of the naturally occurring uranium ore from which it originated, though it would be more concentrated. And nuclear power is the only large-scale energy-producing technology that takes full responsibility for its waste and fully costs us into the product, which is something that I think rarely gets talked about. The financial provisions are made for managing all kinds of civilian radioactive waste, and the cost of managing and disposing of nuclear power plant waste typically represents about 5% of the total cost of the electricity generated. In terms of volume, the IAEA, so the International Atomic Energy Agency under the United Nations, estimates that the disposal volume of current solid high-level waste is approximately 22,000 meters cubed. For context, this is roughly equivalent to a 3-meter tall building covering an area the size of a soccer pitch. So People keep talking about the volume, the nuclear waste disposal issue, but it's actually a very small volume. And as I said, that's because it's such an energy dense source of energy. That's why it's amazing. In terms of climate change and air there, almost all the proposed pathways to achieving deep carbonization suggest an increased role for nuclear power, including those by the International Energy Agency, the MIT Energy Initiative, the U.S. Information Administration, and the World Energy Council. In terms of the climate change impact from nuclear, so the IPCC has wind at 11 grams of CO2 per kilowatt hour, nuclear at 12, hydro at 24, geothermal at 38, solar concentrated at 27 to 48 for utility, biomass is at 230, natural gas is 490, biomass co-firing is at 740, and coal is by far the highest at 820. So just to put that in perspective, nuclear is 12 grams of CO2 equivalent per kilowatt hour, where coal is at 820. So a huge difference there. And that's why in the IPCC 1.5 degrees special report, they stress that rapid decarbonization of the electricity sector will require nuclear power. And I keep hearing that it's a long time to deploy nuclear and that it can't be deployed fast enough. But actually, case studies on the fastest way to decarbonize national economies show that nuclear was a pathway to the fastest top 10 examples, including Sweden from 1976 to 1986, France from 1979 to 1989, and the United Arab Emirates from 2010 to 2020. So it's in all the fastest ways, it's nuclear that's actually getting us to decarbonize national economies. In terms of land use, solar uses 100 times more land and wind up to 300 times or more land for the equivalent energy production. So that's why when we talk about the environment, the land footprint is huge as well. It may not seem so from having solar panels on houses, but when you get it on the industrial scale, the density of energy really starts to matter in how you're impacting the environment, the ecology out there. Another thing as well is that the material throughput on energy production equivalent basis shows that wind requires around 10 times more and solar around 15 times more material than nuclear. So again, it's more mining, it's more fabrication, it's more disposal. You need more materials to make the same amount of power. That's going to be more waste, that's going to be more impact on the environment. So things that don't really get talked about. You know, we see the windmill out there, we see the solar panel out there, and we think it's clean, but we have to think about the life cycle. How much resources does it require? How much transmission lines does it require? Storage, those are batteries, that's extra materials, that's extra energy. So we really have to think about the life cycle impact from these different energy sources and how they impact the environment. And the major thing here is air pollution kills an estimated 7 million people worldwide every year. So the World Health Organization data shows that 9 out of 10 people breathe air containing high level of pollutants. So the do nothing option, or the path we're on, is seeing an increase in fossil fuels being burned. So we can't continue on the same path we're doing. We're shutting down nuclear power plants in Germany. We're shutting them down in the States. There's not the investment needed in them. This is the number one thing we need to do if we want to reduce the impact on the environment, if we want to save people's lives that are dying every year from pollution, if we want to be serious about climate change. There's no other option. We have to start looking at nuclear power. And people keep talking about batteries, people keep talking about producing solar and wind, but it's not doing what it needs to do. Nuclear fusion is out there as well. We have these 4th generation nuclear fission type of reactors out there. These are the things we need to start to invest in, to get serious in. We can't be talking about renewables. We need to talk about clean energy if we're serious about reducing pollution worldwide and about getting the number of deaths down. There's a number of nuclear resources out there, so there's a great number of books. For example, nuclear power, what everyone needs to know, campaigning for clean air, whole earth discipline is a really good one. Power to Save the World is an awesome resource. And a new book that came out recently is A Bright Future. These are all great books that talk about how nuclear can be part of the solution. There's a World Health Organization. There's a World Nuclear Association. There's just so many online resources out there. And I just wanted to end off with two quotes. So, nuclear power is a potential safety threat if something goes wrong. Coal-fired power is guaranteed destruction, filling the atmosphere with planet-heating carbon when it operates the way it's supposed to. So that's Bill McKibben. And the last one I want to end on is, in thinking about nuclear power safety, one should always ask, compared to what? And the answer is compared to coal, the world's dominant and fastest growing fuel. The leading cause of climate change, the fuel that kills 1 million people a year. Compared to that. That's from A Bright Future. So that's really my summary. I know it's probably too technical in some areas and not technical enough in others, but I hope that answered some questions and hope it helps.